Yeah, admit பண்ணப்படுங்க. A very good evening to one and all present. With immense pleasure and pride, on behalf of Department of Electrical and Electronic Engineering, Krishnasamy College of Engineering and Technology, I warmly welcome you all to the AEC Atal sponsored 6-day online faculty development program on emerging trends in digital twin technology for hydrogen production, storage, and transport. Let us begin this auspicious academic program by innovating the blessings of Almighty for the successful conduct of this FTP. Now, it is my proud privilege to invite Dr. C. Kalevani, Coordinator of Atal FTP, to deliver the welcome address. Please, ma'am.
Thank you, sir. Honorable Chairman, Dr. K. Rajendran, sir, esteemed Secretary, Mr. N. Vijaykumar, sir, distinguished CEO, Dr. R. Kannan, sir, Dynamic Principal, Dr. G. Ilango, sir, esteemed Vice Principal, Dr. K. Raghu, sir, respected Administrative Officer, G. Balakrishnan, sir, our beloved HOD, Dr. S. Shivashakti, sir, esteemed resource person, dear participants, and distinguished guests. A very good evening to one and all present here. It gives me immense pleasure and privilege to extend a warm and cordial welcome to you all on behalf of Department of EEE, Krishnaswamy College of Engineering and Technology, to the AICT Atal sponsored 6 days online faculty development program on emerging trends in digital twin technology for hydrogen production, storage, and transport. We are deeply grateful to AICT Training and Learning Academy, New Delhi, for sponsoring this program and for their continuous support in enhancing the professional competence of faculty members through high quality initiatives. The present global scenario, the transition towards clean and sustainable energy system has become inevitable. Hydrogen energy, combined with advanced digital twin technologies, plays a crucial role in optimizing production, storage, and transportation systems. This FTP aims to provide participants with valuable insights into cutting edge research, industry practices, interdisciplinary applications in various emerging domains. We are honored to have with us eminent academicians, researchers, and industry experts as resource persons who will share their expertise and experience over next 6 days. I'm confident that this program will be highly beneficial and intellectually enriching for all the participants. I would like to express my sincere gratitude to our respected management, patrons, organizing committee members for their constant encouragement and support in making this program possible. Once again, I extend warm welcome to all the participants from various states, Andhra Pradesh, Maharashtra, Kerala, Telangana, Puducherry, and all regions of Tamil Nadu like Chennai, Coimbatore, Madurai, Salem, Vellore, and Kannur. And I wish everyone a fruitful and successful learning experience. Thank you, one and all.
Thank you, madam, for the warm welcome and insightful remarks highlighting the significance of this FDP and the role of emerging digital twins technology, sustainable hydrogen streams.
Thank you, sir. Now, it is indeed an honor and privilege to invite our respected principal, Dr. G. Ilango sir, to deliver the felicitation address.
Thank you, ma'am. Most reverend Chairman of Krishnasamy Group of Institutions, most distinguished Secretary, CEO, most respected Vice Principal, Administrative Officer, Convener, Coordinators, heads from various departments, and my dear faculty members, happy evening all. I hope may you all be blessed by God Almighty. I am indeed delighted to be with the honorable members of this great forum. This program is to you have incredible ideas and fascinating on hydrogen production and its storage. This is a time to thank AICT Training and Learning Academy Atal for having sponsored to conduct this faculty development program on emerging trends in digital twin technology for hydrogen production, storage, and transport, which means digital twin technology is evolving from static digital replicas to dynamic AI augmented digital ecosystems that enable deeper insight, safer operation, and cost effective scaling of hydrogen infrastructure. These trends are accelerating hydrogen's transition into mainstream energy system by improving efficiency, reliability, and financial predictability. There is a lot of hydrogen usage in several industries and different other fields. Exclusively, hydrogen fuels are highly used for heavy efficiency and low economical costs. In near future, hydrogen definitely
might
might
occupy
occupy
the
the
most
most
space
space
as
as
equal
equal
as
as
electrical
electrical
energy.
energy.
For
For
running
running
the
the
engine
engine
and
and
its
its access, hydrogen as a clean and versatile energy carrier holds the promise of transforming our energy landscape. By focusing on this production, safe storage, and efficient transportation, this FDP definitely creating a vital platform for sharing knowledge, innovation, and collaborative learnings. Many researchers are having eye on hydrogen production and its running. Now I am feeling good to be the part of this program and extend my warm greetings to all the participants. Besides, I would like to render my special thanks to our management for having given the permission to conduct this outstanding event. On behalf of my ward and all present, I would like to congratulate the organizing committee for their meticulous planning and execution, where at the speaker's involvement and acceptance had been great to share their views in this FDP. My special gratitude and wishes to Professor Dr. Kalaivani for her complete effort taken to conduct the program successfully. Have a nice day, all. Thank you.
Thank you very much, sir, for your inspiring and visionary felicitation address. Your words have truly motivated us and have set a right tone for this FDP on emerging trends in digital twin technology for hydrogen production, storage, and transport. With this, we are confident that next 6 days will be intellectually stimulating and professionally enriching for all the participants. Now, I request Dr. D. Periyaragar, Associate Professor, Department of EEE, to welcome the Chief Guest for Session 1. Thank you.
Thank you, ma'am. Advancement in power electronics, smart grid, and renewable energy system are shaping the future of sustainable electrical engineering. To enlighten us with global perspective, cutting-edge research insight, and real-world application, we are privileged to have a distinguished expert with us today. It is our great honor to introduce Professor B. Sanjeevkumar Electrical Power Engineering at the University of Southeastern Norway. He earned his PhD in Electrical Engineering from University of Bologna, Italy in 2012 and has authored 750 plus international research publications. Professor B. Sanjeev Kumar is a fellow member of IEI India, IET India, IET UK, and European Academy of Science, a lifetime achievement awardee, and is listed among the world top 2% of scientists by Stanford University since 2019. He is also recipient of IEEE System Council Outstanding Service Award in the year of 2025. We are indeed fortunate to have such an eminent academician, researcher, global leader as resource person today. Sanjeevkumar sir.
Hello, could you able to hear me?
Yes, sir. We could hear.
Oh,
Good
thank you
evening,
very much.
sir. Good evening,
evening.
sir.
Okay,
How are you, sir?
I'm fine. Thank you very much for this invitation, and I thank to the hosting institution and partially to my colleague Dr. Kalevani for special invitation because of Dr. Rajambal from Pondicherry Engineering College, where I graduated my masters. Thank you very much for this wonderful evening and giving him an opportunity for interacting with you all. So here I like to present what we have done with our own researchers and PhDs, masters, and postdocs who work with us for a long time. And I like to present my experience, what I gained through several research activities, funded projects we have done from the past. Before I start my presentation, let me introduce you about my university.
Sure, sir.
So could you please confirm my slides are visible for you?
Yes, sir. It is visible.
Well, thank you very much. So I am basically from the University of Southeastern Norway, from the Faculty of Technology, Natural Science, and Maritime. We call it as a TNM. And this is the Norway, which is more horizontal or vertical, which is close to the Sweden and in the North Sea. So about my university, we have around 8 campuses in the southern eastern part of Norway. I am basically from Porsgrunn, and it became a full university in 2018. All the 8 different colleges combined together become the fourth largest university in the Norway. About 700,000 citizens we are serving, and the capacity of student is currently more than 18,000, and we have more than 2,000 plus employees. It's old statistics, and about 88 bachelor programs, 44 master programs, and 8 PhDs in 8 different campuses. As I said, I am belong to the electrical engineering department. We have a bachelor program for 3 years, master program for 2 years, and PhD minimum 3 years program. And this is the beautiful view of the campus, which is around surrounded by various mountains. And we have very good facilities, well connected with industries. We have a nearby industrial park, which is called Hydro Helen. You can Google. More than 100 plus industries are located in collaboration with our institution. And most of our projects are focused towards sustainable renewable energy systems, which includes hydropower plant, because more than 1,000 hydropower plants are available across the country and having a more stable electricity of 99.9 percentage clean energy systems. And we have different research groups focused towards power, energy, smart entrepreneurships, modeling, control, etc., or our specialization in the department. And most of our research activities are funded by the government of Norway, from the Norwegian Research Council, or from the private industries or regional authorities. Our close collaborators are SINTAF, which is the largest research center from Norway and across Europe. And we have a close collaboration with Equinor, which is the largest offshore wind technology developers, and local municipalities, which includes Porsgrunn municipality and Skian municipalities, ABB. And of course, we have challenges towards renewable energy is our goal, and benefits towards the society. And these are some of our facilities available in the campus for executing the task in collaboration with the industries. And these are the real offshore oil and gas facilities, which on the academic concepts, the students will be working on oil and gas products, on process automation, control, etc. As I said, we are running many projects which are in close collaboration with the industries, which includes hydrogen as a powertrain for ships, ferries, etc., and close collaboration with Statnet. Statnet is the largest transmission and distribution operator. Of course, we are working in India in many developments on transmission distribution in collaboration with the government of India. We have also a close collaboration with the National Renewable Energy Labs from United States. And if you want to know about more my university, you can visit the website. Here I like to present one of the concept which is invited by IEEE Industrial Electronics Society for the IECON presentation, which I like to give you an overview how we are working more closely with fuel cell as a powertrain for electronics technologies. So I will be presenting about a common concept. Many of you know what is an electric vehicle. I like to give you an overview about the future developments, how these technologies not only includes batteries. Currently, we use more batteries and charging techniques, but in the future, fuel cell will dominate all these powertrain aspects. As look at the market currently, Nissan, Chevrolet, and Tesla are the big players in a hydrogen-based electric vehicle. Started with BVC model, I mean battery vehicle modules. But there is another silent manufacturer which is called BYD, which is very popular from Chinese market, and they have been dominating the world because of technological readiness and manufacturing capabilities. If you look at EV, EV is a common term, but where it come from? It come from International Electrotechnical Commission, Technical Committee 69, which is the basic resources for creating electric road vehicle prototypes. Why these EV plays an important role? Because based on the classification, what type of energy source, storage, and what type of electronics converters use, they are classified into battery electric vehicle. We call it as a BEV, purely run by batteries. Then we have hybrid electric vehicle, which is an hybrid module as a combinations of batteries and fuel cells, and of course supercapacitors or ultra capacitors. Then currently in the market, we are using hybrid electric vehicle. In the future, it will become an hybrid electric plug-in models, because where we use not only the electric grid, of course, we use electrolyzers. And the future, as I said, fuel cell going to dominate the transportation systems. And the most important aspects in terms of current expectation is towards wireless charging. But there are a lot of drawbacks in wireless charging infrastructure. If you look at the power from the grid side, an example which is around through 3.28 kilowatts from the DC grid, which is given to a two-stage power electronics converters. One is going to convert this DC into high voltage AC, DC voltage, which it's like a step up or step down operation, depends on the requirements. Then we are giving to a high frequency inverter, which converts all these DCs into a AC signal, which is not like a conventional AC, a high frequency AC, which is going to be around 3.13 kilowatt. You can have a look, around 1.5 kilowatt is the last. And this is given to a primary coil, which is called a transmitter, which has an inductor and capacitors, or as a simple transformer. And this is the wireless module available on the surface, whereas the secondary part will be available on the electric vehicle. So the electric vehicle will have a receiver or a secondary coil, which is going to absorb the power around 3 kilowatt capacity. So we are going to lose around 1.3 kilowatt capacity. Then at the powertrain of the electric vehicle, the available capacity is only 2.91 kilowatt. Actual power generated is 3.28 from the grid. So you can have a look, overall efficiency is going to be 88.8 percentage, whereas the loss is near to 13 percentage, which is pretty high in electric power systems, because these are due to the switching losses, conduction losses. Moreover, the design of high frequency coils, which will have also magnetic losses. These losses needed to be compensated. So still now, wireless charging is not more attractive due to these reasons. About batteries, currently all the electric vehicles are focused towards batteries, but most of the batteries we are looking on flyaway or runaway due to firing, because there are some guidelines which is not being used by the manufacturers. Where these guidelines come from? It comes from Advanced Battery Consortium, which is called US ABC from United States. There are some guidelines to design the primary goal, secondary goal, to design the batteries. So in case of energy density, which is around 135 for the midterm, for long term is 300. Specific energy is calculated with respect to 100 percentage of WH per kg, which is around 80 or 200 for long term. Power density is 2 to 50, and for the long term is 600. Specific energy is calculated for 200 watts per kilograms, where 150 for midterm, 400 for long term. Lifespan of the battery is around 5 years, and for long term is given around 10 years. Life cycle for charging and discharging will be around 600, now extending near to 1000 is possible with the EV currently available in the market. And the price of the batteries per kilowatt hour is around $150 less for midterm, and long term is around $100. About the operating temperature is merely around minus 30 degree to 84 degree centigrades in consolidated operation between midterm to long term. And charging is always like less than 6 hours for small vehicles, and for long term goal is around 6 hours, which is pretty high. And about fast charging, which is a reason attractions in electric vehicle with the batteries with respect to the state of the charge, which is around less than 30 minutes. Still, we are not having such facilities. About secondary goals is always available, because if even the battery is not used in service, self discharge. So less than 15 hours is the minimum requirement, either for long term or for the midterm. Efficiency typically between 75% to 80%. Obviously, battery doesn't require maintenance, and abuse to the resistance are tolerable, and thermal losses, which is around 3.2 watts per kilowatt hour. These are the guidelines given for the manufacturers to manufacture the battery for better qualities. And about the batteries, I can give you some examples which are used in practice. Particularly if you look at C30 model and E4 modules, they are having almost more near efficiency between 95 to 93 percentage. So if you decide for the efficiency, 95 percentage is good, but the usable energy is only 22.7. If you look at a little less efficiency, but you can get more usable energy capacity in kilowatt hour is in E6. So it's a trade-off between the efficiency and the usable capacity of the batteries. And about in the future, as I said, we are moving towards all fuel cell, fossils storage tank into DC grids, because to charge all these batteries in the future is required. We have different levels of batteries. Here I have shown until 600. Now the scales are rise up to 1200 to 1800. And in these three level scales, the current can vary from 36 kilowatt to power can vary from 36 kilowatt to 240 kilowatt capacities, and the current can vary from 80 to 400 ampere capacities. But the scale, as I said, has been increased now to 1200, next 1400. In the scales of 400, DC microgrids are required. About power electronics converters, many configuration what I shown here are already available in the literatures, which are widely used in practice. So if you look at this converter, which is called a universal DC to DC converter, which has a combination of, you can have a look, it's a parallel combination of two buck converters connected with one boost converter. So a combination of increasing the current can be done here, and whatever the available voltage at this device will be increased to a higher level. Again, it has been stepped down by using a buck converter. So buck converter is a voltage to current converter. On the input side, you'll have a higher voltage. On the output side, the current will be higher. So for the charging applications, we use this combination to enhance the capacity. What is the drawback? Limited duty cycle combinations. Even though we are increasing the current to the higher limits, and the devices can execute long conduction angle, which increases the conduction losses, and overall efficacy of the system, even if you increase the current, will be limited by conduction periods. And other aspects, the novel configurations are available in real time with even for a fuel cell tank power applications, where we can replace these batteries by fuel cells on either side, or one side with the battery, one side with the fuel cells, and one side with the batteries, and keeping the propulsion system, which is a three-phase induction drive open winding. So you have been seeing the configuration, which are having one side power supply, another side will be having a start point. But these configuration, we remove the start point and we connect another inverters, which can be powered either from electrolyzers, hydrogen power systems, or from the batteries or supercapacitors. What is the advantage? The power of the power source will be reduced by 50%. So we don't want 100% power supply. And the redundancy is that if one inverter fails, still we can run with 50% power. And the most important is that since there is no star point in the network, we reduce homopolar component. There is no circulation of zero sequence or homopolar component. So we don't need to think about filters or resistors to connect with the ground to compensate all these homopolar high frequency components. Other side, we can able to make it as a one power supply, which are connecting on either side. Still, it is a open winding. The disadvantage is that the power needed to be 100%. And if you lose even one inverter, we can drive with another inverter. Since both the sides are connected to the same source, there will be a flow of homopolar components, which is high frequency signals, which can produce huge torque and oscillation in the systems. So we need to design filters for homopolar components. Other side, we can think about interleaved boost converters, which is a combinations of the two boost converters connected in parallel to enhance the current capacities. On the input side, we have a diode bridge rectifier, which can control the input power supplies or AC grids. Since this is an uncontrolled bridge rectifier, the efficacy of the delivered DC power will be limited. And we are using a classical boost converters. Again, it is limited by duty cycle, but even we increase the current. So there are some disadvantage in controlling the conduction angles, the duty cycle for the maximum utilization. And these all causes more losses and reduced efficiency. Apart from that, we are also having other slow diode controlled rectifiers on the input side. We can have a slow diode controlled diodes. You can have a look. And the full bridge converter here, we are using only two devices which are going to be controlled, whereas upper devices are only a diode, which is called a semi-controlled converters, bridge converter, H bridge converter, which can able to control the DC power effectively from the AC. But as we know, we are using half cycle control by using two MOSFETs or IGBTs. The efficacy also reduces and of course increases more losses on the charging units. Other aspects I as discussed in the beginning in my presentation, wireless charging plays a critical role. Even wireless converters, I mean, these high frequency converters are used for electrolyzers, fuel cells for enhancing the power capacities with the grid or offshore wind or offshore power generations. They are used widely. Here, the idea is to use a full bridge converter, which is a H bridge fully controlled device. You can have a look here. Two devices are replaced by two control MOSFETs and controlling the DC buses. Then we use high frequency transformers in a ratio 1:n. And this power will be delivered to the secondary side, which is an uncontrolled bridge rectifier. Then we connect to the batteries or electrolyzers. That can be an optional option we can use. Again, here the drawback on the front end, we have a efficient power conversion by using high frequency conversion. On the load side, we have an uncontrolled bridge rectifier. Currently, this has been used in practice, even for charging the electric vehicles. So here, as you know, the bridge rectifier, we reduce the power and we create large ripple or oscillation of AC components in the DC. So we need to increase the size of the capacitors so it can produce more heat. Of course, the efficiency is limited. To improve the characteristics, we can able to increase the number of legs. Here is an example of a bridge interleaved boost power factor control. We can able to control the power factor on the input side AC grid by using the inductor, along with extending the angle to the fourth skill legs. I mean, standard three phase is like a three bridge, but we are having four legs here to extend the conduction period and increasing the current capacity to the load side of the batteries or electrolyzers, which are connected for the applications. But still, it's an off control and we have a slow operational diode, can reduce the overall efficiency and increase the capacitor size. But the capacitor size is limited when comparing to the configuration shown in 6. Other possibilities, we can go with wireless configuration by cascading parallel model. You can have a look. An extension of this converter is shown here. So we are cascading two high frequency H bridge fully controlled converters and using two different um, high frequency transformers, which are going to have the same 1:n and 1:n ratio, and they are coupled at the same uncontrolled bridge rectifier. Here we can able to pump up the current to higher levels. Again, it is limited because of the uncontrolled bridge rectifier on the load side of the battery or electrolyzers. So please note what are the applications I have shown here. We can replace the batteries by electrolyzers to integrate with the grid or for the charging units. The most effective is the LLC resonant converters, where we use a fully controlled bridge rectifier. On the transmitting side, we are including a magnetizing inductor and a capacitor additionally, so that we can able to improve the turns ratio. In the previous case I showed you, it's a fixed ratio 1:n, but here we can have a variable ratio n1:n2, so we can have a variable taps on the transmitting and receiving coil, so that we can have a different power scale of power transfer from the DC side towards the battery or electrolyzer. And currently we use the modules which are uncontrolled bridge rectifier. This is a big problem. They are slow transient diodes and are not fully controlled. So we get reduced voltages with much more losses because diodes are slow transient, and the capacitor size needed to be compromised and produce more heat for the batteries. Finally, I like to say either it's for electrolyzers or for hydrogen production interconnected systems, or for batteries, we have options like buck converters, which can able to use to send the power from the motor or to charge the batteries. Other options, we have buck boost converter, which is a two mode of operation. We can deliver the power to the batteries or take the power from the batteries towards the propulsion units. The propulsion unit powertrain can be batteries or can be electrolyzers. So for example, when you apply the brakes in the electric vehicles, you generate a lot of reactive energy or regenerative energy from your motor, and it will be fed back to the batteries. It's very dangerous. That's why these power electronics converters play a critical role in both directions, for driving as well as for regenerative energy generated from the motor. It can be stored in the batteries. Other aspect I discussed is on interleaved boost power factor converter, where we can control the power factor on the grid side, and it has a unique characteristic. So we need to put a EMI filter because high frequency transformers are used, and these are used only for charging. I also discussed on dual boost power factor converters. This is also used along with power factor correction. Here we doesn't require any bridge rectifiers, is used only for charging. And of course, I discussed about full bridge converters with the capacitor filters on the transmitter side with the 0 volt switchings, where we can go for variable taps. By using 0 volt switching, we can able to reduce the noises and of course, the losses. Of course, we can able to use this only for charging. About fuel cell train is going to be a big market in across the globe, and the government of India already declared by 2035 to 2030 to be the largest hub for hydrogen production across the world. And in the context of European Union, already many electric vehicles are deployed as an hybrid model. We use electric batteries along with the fuel cell as a powertrain, and fuel cell is the main powertrain, and batteries are like a substitute modules during the requirements. And the shift between the fuel cell and batteries are automated by using power electronics converters for power conversions. Why fuel cell has a big market? Because it can be adapted for a 50-watt power supply or even for a small 1-watt power supply towards maximum 100 megawatt capacity. The most important is the resistance to the temperature, which can vary between -20 to greater than 800 degrees centigrades. And power scale application can be for small power or large power. It can be a vehicle or grid connected systems. For example, if you are going to use a zinc car battery, which is a typical module of fuel cell, which is not widely used. Currently, we use a proton exchange membrane widely used in practice. So, for example, if you are going to use a zinc car battery, it can be adapted for small power application. Say, example for transportation, small vehicle. And if you are going to use about the temperature, it can be adapted between 80 to 0 to 80 degrees centigrade, and it can be used for the application of less than 50-watt capacity. So this is the advantage why we go for fuel cell. And the production cost of hydrogen is expensive, but the running cost is very effective and maintenance free. These are the major goals for high power application. For example, for a small domestic car, it's okay with a battery, but think about ships, ferries, or very large transportation systems. So in 2026, one of my collaborate company from Norway, Brunwell, we are doing a project on offshore hydrogen production in coordination with other partners from Europe, where the Brunwell company is going to release its first 100% power-driven fuel cell ferry in Nordic Sea. How it looks, powertrains. For example, in case of a fuel cell based powertrain, we'll have a fuel storage for hydrogen. It will given to a fuel reformer with a efficiency of 80% it can able to generate. And fuel reformer is connected to the fuel cells, and the fuel cells efficiency is only 60%. So efficacy of the fuel cells power generation limited by 60%. Here comes the power electronics converters to maximize or to utilize this 60% efficiency very effectively for the powertrain. So we have two-stage power conversion. One is the first stage, we use all these DC to high power DC powertrain requirement within the electric vehicle power supplies. Then it is given to an inverter which converts AC power to drive the induction drives or synchronous drives of the electric vehicle. So efficacy minimum level starts with 80%, which is very effective. By using modern GaN devices or silicon carbide devices, the efficacy can go near to 99%. Apart from the powertrain, we also have luxurious needs within the electric vehicle. All these can be powered from a small power electronic actuator, which is called DC to DC converter with a minimum efficiency of 80%. As I said, for many applications, hydrogen is more expensive. So we look for a combination module. So in a combination module, we can bring batteries and ultra capacitors. If you look at the batteries has a limited lifespan. Currently, lithium-ion batteries are used wide in practice, and the lifespan guarantee is around 8 years, but it's not true. It can be exist by 5 years or a 6 year span, and recycling is a big complex. And in order to regulate the batteries, we have to look always the state of the charge, maintain between 85% to 90%, typical electric vehicle applications. And the most important, it has to be charged from DC. The replacement is an ultra capacitors or super capacitors because it can be charged 1 million times, 10 lakhs times. You can be able to charge and discharge either from AC or DC, irrespective, and the reliability is much higher than batteries. The most important is ultra capacitor or fast transient. What is the meaning of fast transient? In 5 milliseconds, you can deliver the maximum, even 550 megawatt power supplies. Whereas battery is a slow transient, it cannot able to charge or discharge in 5 milliseconds. So ultra capacitors plays a vital role because of its delivery at peak time. So in the future, the vehicles will be propagated along with hydrogen and supercapacitors as a definite modules. If you look at a large powertrain application like ferries, trucks, we need to depend more on fuel cells. So cell is the main powertrain, which is connected to a small actuator for electronics converters to maintain a DC grid, which is around 1200 volt to 1600 volt is a requirement. On the propulsion sides, we will have a large synchronous machines which are connected by using inverters to convert all these DC power to AC. And we can't avoid the AC load, which is going to be around, say, example, 20 kilowatt capacity, will be again driven from the inverters. And we have sophistication requirement is lightnings, etc., which can be around 25 kilowatt. An example can be again driven from a small actuator DC to DC converter. So you can have a look how a complete powertrain module looks with fuel cells, batteries, and supercapacitor integrations. So in these aspects, we have developed many our own power electronics converters from the laboratories where we integrated different renewable energy systems. If you look at conventional modules, we have photovoltaics, wind turbine, and battery, which requires four different converters. Because wind turbine has a AC power, it has to be converted into DC and pump up to higher level to integrate for different applications. So with our multi-port converters, we develop from our labs, it has a multi combinations of our ideas based on circuit theories. We can able to connect one converter with multiple inputs, but for the wind turbine, the power has to be converted from AC to DC, so we need an additional converters. But the application aspect is the same. Our goal is to maintain the maximum power generated from the photovoltaics or batteries or fuel cell or wind turbines, which are integrated to the converter. So if the power are reducing or increasing, we have to be at the maximum power point by regulating all these MOSFETs and IGBT. If you look at the front end, we have a standard buck converter. On the back end, we introduce our boost converter to integrate for higher values. Again, we use another boost converters for integrating another renewable. It can be a battery or electrolyzers, and this can be a photovoltaic systems. Then these converters are triggered at different duty cycles to generate a constant power, which we require a maximum power point. It means that wind turbine can be fluctuating, photovoltaics can be fluctuating, batteries or electrolyzers can be fluctuating at different values, but still we try to maintain a constant power at the load side. Some of the testings has been conducted in real time. You can have a look like a battery module. We make the photovoltaics around 12.5 volts. Currents is regulating around 7.9 amperes, which large oscillations. Whereas the load side, we pump like a battery module because in EVs, we need like 24 volt and 48 volts. And the current regulated for 3.6 amperes. The most important, we are using only 60% of the power by using the duty cycle. So we are not using the 100% power from the interconnected DC links. On other side, we try to pump up the PV voltage to 30 volt, current to 800 milliamps. As the voltage increases, current comes down. On the load side, we drop the voltage to 18 volt and current to 980 milliamps. Here we use only 40% the capacity of the renewables, means duty cycle, only 40% used. All the cases, the current through the inductors are very important. They are periodic, doesn't have any spikes because if it is a battery or electrolyzers, they are easily affected by these currents if there is a small fluctuation. Already CSIR lab in Dehradun and Roorkee are working more effectively on electrolyzer designs. I have collaborated with some CSIR laboratories, particularly in IIT Roorkee and Roorkees, where they are developing the efficiency of the electrolyzers to increase from 60% to 65%. where these are the big challenges needed to be withstand. So power electronics converters play a critical role to maintain all these fluctuations. And this is modules, you can have a look in simulation modules. Obviously, the efficiency will be very high, near to 97 to 98%, but not in real time. The efficiency is limited to 93% because of various switching losses, conduction losses, switching losses, and EMIs. How we develop all these concepts, idea is to start the program. We check the power of the photovoltaic. If it is greater than 0, we go to the next step. We check the power of the PV is greater than output power. If it is okay, then we check the current of the battery is greater than the maximum battery current. Then we connect the photovoltaics, batteries, or electrolyzers to the load. Otherwise, if we fail in the first step, we connect the battery to charge the loads. Or if you fail in the second step, the power is available from the battery and of course from the fuel cells or photovoltaic, but not sufficient for the rated power. So we add all the power and connect to the load. If all the condition is okay, then we check the battery current. If the battery current is greater than the battery current, no, then we check for the state of the charge. If the state of the charge is 90%, it can be connected to the load. Otherwise, we take the power, we charge the battery, then we connect to the load. On these aspects, particularly for fuel cell aspects, we develop new power electronics converters from our own ideas to integrate for higher voltage levels between 400 to 800. For laboratory testings, we withstand around 400. So the interconnected system has a large scale fuel stacks, photovoltaics, and batteries. Why we use batteries? Because if there is an excessive power generated from the fuel stack and batteries, photovoltaics will be stored in the batteries, and during the peak demand for electrification of electric vehicles or DC micro homes or DC homes or existing AC grids, we pump the power from the battery. So in this context, we need a reliable power electronics converters. We introduce a three-state power electronics converters. Why it is called three-state? We have three MOSFETs or IGBTs, and these three devices are conducting in three different states or conduction, so that we are able to generate a high voltage requirement for the common grid. How we develop this configuration? This is a very standard H-bridge inverter, or if you look at a full bridge DC converter in NEDMOG and textbooks, you can find it, where we replace one of the MOSFET by the inductor LX, and on the second leg, we replace it by LY. Or if you look at the power electronics textbook, the same configuration is available in the form of a semi-controlled full bridge rectifier. Then we incorporated the standard boost converter, which is followed in the industries. So we can't avoid the boost converter, the parallel and series combination. Then we integrated by using a capacitor CX and CY. Then we use a specific diode, which is called DZ, make always the current flow towards the diode, and reverse flow is restricted. So that naturally this power electronics configuration, well protected for any short circuit on the load side, will not affect your electrolyzers, fuel cell stacks, or photovoltaics or batteries. What is the idea? When the device is closed, we energize LX. Similarly, when the device Y is closed, we energize LY. As we know, the inductors are instantaneous energy. They are not the storage devices. So when the device is opened, the energy available X will be delivered to CX. Similarly, LY will be delivered to CX, and these two capacitors are connected in parallel. So we add up and deliver the voltage to the load side boost converter to enhance the capacities. So we compared with the industrial solutions and literatures available in the market. Our configuration is always superior even at a 60% duty cycle or utilization of the renewables, which are connected on the fuel cells, batteries, and photovoltaics. We get around 42 times the gain. Once the converter is designed, we look for the gain margin, then we look for the losses before testing into the real time. So the MOSFETs are producing around 16 to 17%, diodes between 4.8 to 5.2%, capacitors around 6%, and the resistance of the inductors typically 9%. So we know the complete distribution of the losses before deployed into the system. Our goal is to maintain a minimum requirement of the common grid, which is around 400 volt. We are near to that, but it's not exactly. And if you look at the voltages across the diodes or forward biased, ensure the requirement of the conduction, what we want. And these are the voltages across the devices, MOSFET, which pumps to 185. Our input fluctuates between 24 to 48 volt requirements like a battery module, but we pump up to the scale of near 400. And the most important is the current through the inductors are very periodic, symmetrical, doesn't have any spikes, which can easily affect the electrolyzers which are connected on the input side. So we always ensure the current on the input side are periodic and doesn't produce any short spikes. The most important in real-time application is these electrolyzers are pumping the power simultaneously, of course, along with the batteries. But we drive the vehicle at high speed, low speed, and of course, or not static operation or dynamic operations. Dynamic behavior is very important so that we regulated the converter for different dynamic operation from a standard scale to a minimum value. The current follows the requirement on the input side, of course, on the load side, whereas the input, all the voltage is maintained at constant values, doesn't affect these regulations. As I said in the beginning, we are not getting exactly 400 volts, which is around 395.2 volts and regulated towards the minimum 206. And the currents are regulated particularly with the inductors from 16.59 amperes towards 4.6 amperes, but in symmetrical characteristics. How we obtained all this value? We regulated with the closed loop control operations, ensuring two devices. We have three MOSFETs. One MOSFET is at a fixed switching range of 20%, whereas others two are conducting at 50% and 35%. So I get around near to 400 volts, whereas for 206 volts, both the MOSFETs are conducting at 35%. So we are not moving away from 50% margin, which is pretty good for controlling all these electrolyzers are very sensitive to small fluctuations. These are the laboratory model testings. You can see the compact size of the converters. We use the components which are readily available in the markets with the standard gate driver circuits. And if the component fails, it can be easily replaced or the complete unit can be replaced. For the more visualized results, you can have a look why we are zooming these results, because to show you that how the modulation of the converters are carried out for smooth regulation of all these currents are very vital. Apart from that, we also worked on our industrial solutions. So quasi-Z source inverters are highly used in forklift applications where high power trains using small electrolyzers or battery banks are used. So in this case, we try to figure out a new configuration, a modified solution. We introduce a switching inductor. We call it a switching inductor because it stores and delivers the energy to the capacitor based on switchings. So here we introduce a new configuration along with the capacitor C2. It become a novel configuration of quasi-source inverter. Idea behind is the switch is closed. We energize the inductor LX and LY and LY2. When the device is open, this energy will be delivered to C1, and the LY and LY2 energy will be delivered to the capacitor CY. All these capacitors will become a parallel operation. So they add up the voltage and deliver to the load side standard boost converter. If you look at a quasi is a source converter, on the lower side is a very standard boost converter. So all the configurations available in industries or from the research point of view, the basic configuration is a very standard buck converter or boost converter. For example, if you remove all these blocks and put a MOSFET, it become a standard buck boost converter. So we are adjusting based on circuit theory and combinations of passive components, new configurations are developed. If you look at the duty cycle, still more, you can have a look. We are not even using 50%, only 30% of conduction or duty cycle is used. It means 30% we are pumping the power. The gain is going pretty good, more than 22 times, which is very good for the power electronics converters comparing to the existing solutions. And the most important, we are using more capacitors. In these aspects, the controlling capacity is very complex because the reliability of capacity is a separate research topic in power electronics. But by using our sophisticated PWM methods, all are having the same transient and they are reaching the steady state value of the voltage design according to the theoretical designs. And if you look at the close fluctuation or ripple content or AC component available in the DC are limited but not more than 1 volt or 2 volt, which is pretty good for regulating IEEE standards and ensuring the reliability of electrolyzers connected on the input side. Of course, we worked on CPIC converters because CPIC converters are highly used in forklift, again, to integrate electrolyzers and battery banks, but their efficiency are limited, power density, of course, limited, overall power trans is limited. So in case we done a new modification by introducing the inductor Ly and the capacitor C2, a new combination, we brought a new modified SEPI converters which can able to enhance high power density. For example, the device is closed, we energize Ly and Lx. When the device is open, these energies will be delivered to C1 and C2 and they become a parallel combination to increase the load side boost converter. So this is a load side boost converter but as an inductor grounded between the positive and negative. So we get a very high power voltage on the load side comparing to the existing SEPI converter. If you look at the losses, the device provides 47% losses and the diode between 13 to 12%, inductors 10%, capacitors 5%, and the combination of other passive components around 0.4%. Typically, we tested all these high power converter or low power scale like 100 watts for safety reasons. We got efficiency around 91.4%. If the power scale is increased, obviously we will be getting around 98% efficiency. The most important is power electronics converters are not linear operation when integrated with all these electrolyzers or batteries because they are highly non-linear. We try to figure out non-linear operations, of course. So we call it as a continuous conduction mode, which is a linear operation. Discontinuous mode of operation, which is a highly non-linear because the frequency goes to very high level, greater than the switching frequency. For example, we operated around 50 kilohertz, 50 kilohertz switching frequency, but now we pump to near to 150. So here, if you look at like all the renewables from the electrolyzer or work like a battery modules, and the currents are regulated as expected, and the voltage pumps to 172, and the current through the inductors are periodic. This is very linear operation, but during non-linear, you can have a look, the diode giving two different voltages. Already I showed you in forward bias condition, the voltage pumps to one peak, but during non-linear operation, it pumps to 92 and to 152 volts, which ensures highly non-linear operation of the power electronics converters. And the current through the inductor goes to the peak and comes back to zero. These also ensures that the discontinuous mode of operation is going on and the load voltage still regulated to 92 volt, which is pretty good for dynamic behavior of the converter. So from our labs, we developed more than 150 configurations, which are addressed in IEEE journals in an open access model. Anyone can download and read around 60 to 100 page papers, which gives you more idea what we have done on this configuration. So our development are focused on number one, which is a switched capacitor based, switch inductor based, multi-level converters and XY families. And we compared with the standard solution, which is a resonant converter I discussed in the beginning of the presentation. They are average with the reliability. Cost is very high because they use high frequency transformers. And because of using high frequency transformer, they has freedom to have different switching cycles, tunable ratios, high power transfers are possible with soft switching. But the disadvantage, bulky in structure, magnetic losses can be produced in the coupling, and they use only for high power. But our converters, what we develop, can be adapted for low power by using switch capacitor family, switch inductor family, multi-level converter family are used for high power applications, and XY family in overall comparison can be used either for low power or high power. With an advantage, we use only one MOSFETs with extendable structures. I showed you like quasi Z source and SEPI converter as an example, but we have done many complex converters. For the limited size time span, I can't be able to elaborate more. And if you look at the reliability is very high, cost is average, high efficiency. The disadvantage is we use more diodes. That's why we cause more discontinuous current. I showed you an example still in during discontinuous of mode of operation. We are able to regulate around 92 volts. Apart from DC converters, we also work on AC converters, which having a six-phase systems where we can able to use electrolyzer as a one source and batteries, supercapacitors, along with photovoltaic module. So we can have four different power supplies integrated to the same systems for high propulsion devices like a multi-level converters. And these converters advantage, one fails with three we can able to run. At the worst case, if three inverter fails, we can try with one inverter, but the power reduced to 1/4. If all are four available, we can try with 100%. But with one, it is going to be 1/4. What is the advantage? The phase voltage is like a multi-level inverter, which goes to 9 level. The fundamental voltage will be having a pure sinusoidal structure. and the line voltage can pump up like an 5-level inverters with more sinusoidal characteristics. In conclusion, I like to emphasize more on how the fuel cell will be having a futuristic goal. So it will be a main powertrain for low-cost vehicle, become a prerequisite because with batteries we can't run for a while. Currently, lead acid batteries are not available in purpose is gone away. Lithium ion batteries are currently used with a limited lifespan, and there are resources to overcome to find new technologies for recycling, and still not reliable solution is available. In 2030, around 250 billion batteries will be revolving around the world. There is a big challenge for batteries to grid to battery challenges, and these can be overcome by using fuel cell technologies. When we integrate with fuel cell technologies, there is another challenge we are going to integrate will be high voltage chargings and commercial aspects of developing wireless chargers. About voltage instability may come, and harmonic and voltage sags will arises by integrating all these renewables, particularly with the high electrolyzers. Then smart grid technology needed to be employed. In the future, all these vehicles, particularly from the battery concepts, we are going to connect with the grid to the vehicle by adapting smart metering technologies. We'll be discussing in my second lectures in few days time, where I will show you how we are integrating IoT sensors, how we integrated smart meters on the topics, and this also creates system stability penetration issues. So for the future research, there is a big goal for energy management algorithms by using AI solution, artificial intelligence solutions, and of course there is a demand to increase energy bond algorithms. Thank you very much for your attention. If you have questions, I'm happy to respond.
Thank you, sir.
Thank you very much.
Dear
I'm ready
Professor,
for.
Sir,
you have any queries?
participants, you could post your queries in the chat box.
Dear Professors, you have any queries? Dear Professors, you have any queries? Kindly post your questions in the chat box.
Sanjeev, sir?
Yes.
Sir, how about the funding proposals or agencies which could be approached? Any ideas?
I'm working from Norway. I don't know how in India you have to think about DST, but in Europe it's mostly for Norway is Norwegian Research Council funding. We have collaborations for India, Nordic fundings are coming up. You can find it in online. These are the funding resources available for these projects. I mean, from the context of Norway. From the context of Europe, we have European Horizon funding calls. It's tie up between the government to government. So the international projects from Norway are directly connected between the government of Norway from the Ministry of Higher Education and Research towards the Ministry of Education from the government of India. So a high level they decide, and obviously I believe every 2 years the calls comes between Norway and India. And about European contest, every year there is a call from Horizon funding call. It's a collaboration between Horizon Europe, the European Commission, and the Department of Science and Technology from Government of India. So you can visit just by Google EU Horizon. Every year the call comes between India and Europe.
Thank you, sir. There is a question from Vincy Pond. She's asking about your link for your IEEE papers, sir.
I can share you in an email. Is possible, or you want now?
Okay, ma'am, sir will be sharing through mail. I'll post in the chat box in the next sessions, ma'am.
But
Is
you
it?
can,
Yes, sir.
if you want, I can, because it's readily available in the online search. You can find the detail.
Okay, sir. Okay.
And the topics which I discussed today is readily available for free downloading, because we had a project from the Denmark and we paid from Denida funding agency. So we made it intentionally open access because it should reach everyone. Otherwise, you need to pay $25 to download the papers. So I can share you the link where you can find all my activities.
Sure, sir.
Any more questions? I expect, because I finished a little quicker, because I look for a lot of questions. That is always, I like it, because somebody is always presenting is not good, because many institutions from India are inviting, and it's very complex for us also. Every time, but it's always obvious. If you ask a lot of questions, I'm very happy.
Participants, do you have any queries? Now it is my proud privilege to invite Engineer J. Jayakumar
Any
to
questions?
deliver the
Yes, sir. I have one doubt.
ordinance.
Can I ask, sir?
Yes, why
Yes,
not?
sir.
sir.
Yes, sir.
I think it is echo. Is it audible?
Yes, sir. You're audible. Please proceed, sir.
Actually, in IEEE, I published some paper, but it is not downloading, or sometimes it is not opening, sir.
This issue, you have to contact the IEEE support team. I don't know, but anything in IEEE, if your university is not having a subscription, you need to pay $10, $15, or $25 per download. If, for example, in my case, my university has a full subscription, so I can download any paper free of cost, because university pays. So this may be a one issue. Other issue, if you still face some problems, please, there is a 24 hours online support in IEEE, customer support in online chat. You can discuss directly.
If I want to subscribe, means I need to subscribe whole, or specifically some department specific can be subscribed, sir.
For example, if you want to have Power Electronics Society paper, you have to subscribe Power Electronics Society. If you want complete IEEE, then you have to pay for the complete IEEE in general. Then you can download conference papers, journals, etc. If you want to one society, for example, if I take a membership only for Power Electronics Society, I can download only from Power Electronics. Other society is not possible.
The amount is different, sir?
Yes, for academic universities, in my understanding, there will be a consolidated reduced price. The university library has to discuss with IEEE and make an agreement for subscription.
Is it possible for me? Possible? Hello, sir.
Yes, I'm listening.
Is it possible for me to subscribe individually?
Yes, you can go to IEEE Explorer, take a basic membership. Along with the membership, you have to take a society membership. If you take a society membership, you can do it only for that society papers downloading, but not all the papers. All the papers is very expensive. You can't take a membership. It's not easy.
Okay.
That's
It is
better through university.
yearly subscription, or it is a lifetime, sir?
Sorry?
It is yearly subscription, or it is lifetime?
It's a
Sir,
yearly subscription, yearly.
Okay. Thank you.
question கேக்கு.
Thank you, sir. Thank you.
Yes.
Now it's my proud privilege to invite Engineer J. Jayakumar as
And
Assistant
if there is no
Professor,
question,
Department
thank you
of
very much for
Electrical
your
and
invitation.
Electronic
Thanks to
Engineering,
Dr.
to
Kalaivani for
deliver
inviting
welcome
me.
address.
And
Please,
last but not the least, currently I become a Vice President of Education in IEEE System Council which is a part of the IEEE network, like a society, is a council. So if you have an IEEE membership, you can join because IEEE System Council is free of cost. And we have a lot of initiatives in the System Council for conferences, journal publication, particularly on education initiatives. You are always welcome to contact my chairs. All the informations are available in the website, and promoting educational activities of inviting of our distinguished lecturers. We provide the economic transportation. Maximum $1,500 will be sponsored from the council. As I said, if you are inviting any of our distinguished lecturers, which is available in the website, you can invite to your campus if you have an IEEE System Council. It's free of cost. You don't want to pay additional money if you have a IEEE chapters or IEEE members and student members. Then you can invite us, invite our colleagues from the System Council. There are many electronic resource libraries. We have recorded presentations from various distinguished lecturers from our own council, of course, from other IEEE societies and invited experts. These all you can utilize for your developments, which is free of cost. Thank you very much.
Thank you, sir. Hearty congratulations for being winners and also proud of you. Let's invite Jaykumar, sir, other part to deliver the time for your wonderful session, sir.
Thank you.
So, good evening, everyone. So, it is my privilege to present the vote of thanks at the conclusions of the first session of the successful online AICTE faculty development program on emerging trends in digital twin technologies, hydrogen production, storage, and transport. First and foremost, on behalf of the organizing committee and all the participants, I extend our heartfelt gratitude to our esteemed chief guest, Dr. Sanjeevkumar sir, for accepting our invitation and sharing such valuable insights. Sir, your expert thoughts have truly set a high benchmark for the rest of the program and have inspired everyone attending. Thank you, sir. We sincerely appreciate all the participants for joining the FPP with great enthusiasm, engaging and worthwhile. Thank you, sir.
Thank you,
very
Jaykumar,
much.
sir. Thank you,
Thank
Jaykumar,
you.
sir. Thank you, sir. Thank you, Sanjeev,
Bye.
sir.
Thank you. Bye.
Nice meeting you. Sir, just stay online. We need to take screenshots, sir.
All the
Sanjeev, sir.
participants, please unmute your camera. Dear participants, please unmute your cameras.
Dear participants, turn on your camera.
Dear participants, please unmute your cameras. We had a photo session. Thank you. Thank you, participants.
Thank you, Sanjeev sir.
Thank you, Sanjay sir. Thank you so much. Participants, please switch off your cameras. இதோ ஷேர் பண்ணுவோம் செஷன் ஒன்னோட.
Participants, feedback will be only shared in this chat box, will not be shared in the WhatsApp group.
Pandikumar sir. Sir Pandikumar sir. கால் பண்ணேன். Dear participants, please wait in the. Soon one feedback link will be shared in the chat box. Please fill the feedback.
Sir, am I audible?
Yes, sir, you are audible.
Sir, we start the session.
One second, sir.
Okay.
Now, it is my proud privilege to invite Engineer J. Jayakumar, Electrical and Electronic Engineering, to deliver the welcome address for the second session and introduce our second session guest, Dr. A. Pandikumar sir.
Good evening, respected dignitaries, esteemed faculty members, dear participants, and distinguished guests. It gives me immense pleasure to welcome you all to this online AICT Atal Faculty Development Program on emerging trends in digital twin technologies for hydrogen production, storage, and transport. This FDP is aimed at enhancing teaching competences, fostering research insights, and promoting cutting-edge technology among academicians, researchers, and professionals from across the country. We are truly honored today to have with us an eminent leader whose experience and contributions perfectly align with the goals of this program. Our chief guest for today's session is Dr. A. Pandikumar. He is currently working as a principal scientist in Central Electrochemical Research Institute, Karaikudi, India. He obtained his PhD in chemistry in 2014 from the Madurai Kamaraj University. He successfully completed his postdoctoral fellowship from 2014 to 2016 at the University of Malaya, Malaysia, under a high impact research grant. He is in the top 2% of scientists list in the world database released by Stanford University, US in 2024. Recently, he has received the prestigious Young Scientist Award for 2023 from the Academy of Sciences, Chennai, Tamil Nadu, for his pioneer contribution to solar energy conversion. Also, he has been elected as a fellow member of the Academy of Sciences, Chennai. He is a life member for advancement of electrochemical science and technology. His current research involves the development of novel functional materials for photocatalysis, photoelectrocatalysis, dye-synthesized solar cells, and water splitting applications. His result outcomes were documented in 160 peer-reviewed journals, including 14 review articles, and also have 9,700 citation with a high index of 61. We are deeply grateful that he has taken time from his busy schedule to join this online FDP and share his valuable insight with us. Sir, your presence is a source of inspiration and motivation for all the participants tuning in from different parts of the country. Ladies and gentlemen, it is my privilege to invite our chief guest, Dr. A. Pandikumar, to deliver his presentation. Thank you.
Sir, thank you, sir. Thank you for your nice introduction. So I have chosen the topic photoelectrocatalytic water splitting, a journey from lab scale to prototype. So usually the photoelectrochemical water splitting will use it to produce green hydrogen. But the green hydrogen by using the sunlight still now at the lab level investigation itself. So we want to go for commercialization or scaling up the hydrogen production. We have to work beyond that lab scale. So in this case, I'm just going to show how we have started with the lab scale investigation and how we moved to prototype fabrication and this performance testing. So before moving to my lecture, I just want to give small introduction about my institute. So I am from CSIR-Central Electrochemical Research Institute, Karaikudi. So this institute is established to mark the occasion of our independence. So, Valalagappa Chettiar, he offered 15 lakhs rupees and 300 acre lands to establish this research institute at the remote place of Karaikudi. So, this is our 11th National Laboratory. So, we are offering the final year project for BTech, MTech, MPhil for all the students. They can do their final year project here. For faculty member, you might just make use of this link for avail that the sophisticated analytical instrument facilities. In addition, academic side, our institute offer PhD program under ACSER and BTech program under Anna University. So this picture is taken during the foundation day. This picture is taken during the inauguration of our institution. Then this is our main entrance. So our institute activity is mainly electrochemical research institute. So according to that electrochemistry, so our divisions can be classified into corrosion and material protection, electroplating and metal finishing, then electrochemical power sources, electroorganic and materials electrochemistry division, electrochemical process engineering, and the electronics and the electrocatalysis division. So I am belongs to electroorganic materials electrochemistry division. So in this division, I am leading that solar energy materials research lab. So here our group is mainly working on dye-sensitized solar cell, perovskite solar cell, electrolyzer for hydrogen production, photoelectrochemical cells for hydrogen production. Recently, our group has entered into that hydrovoltaic devices. So when we talk about the solar cell, we are developing several components, especially the paint formulations also we are developing. So when we talk about the electrolyzer, we are using membrane-based electrolyzer and membrane-free electrolyzer. So in our India, one and only group working in membrane-free electrolyzer, that is my research group. Then this hydrovoltaic device that will be able to produce electricity during that heavy rainfall and flooded condition. So from that we can be able to harvest electricity. So this is my research team. So these are all group alumni. So it's like why I have chosen this particular topic, there is a conference held in Paris in the year 2016, April 2022. So there 195 countries, the prime minister, they have participated and discussed and argued about that the global issues. So then finally they have find that the climate change is a big issue, so that we have to stop that climate change. For that they have signed the agreement. According to the agreement, this agreement will cover the climate change mitigation, adaptation, and the financing for such a related activity. Then our this agreement is entered into the force on 4th November 2016. Once back to our Prime Minister to India, he announced a national e-mobility mission. This national e-mobility mission is nothing but it is switching from fossil fuel based mobility to e-mobility. So this e-mobility, we are using that the plug-in type electric vehicle. It contains the battery pack, battery management system, high voltage cable, and a specially designed motor. As like charging our mobile phone, we can plug in and we can charge. Then we can make use of it. So you just look at this. This is the surveys taken between January to December 2020. So even it is a pandemic period, almost 17 lakhs vehicles, e-vehicles are sold out. Then when we talk about the middle class people in India, January to December 2021, so it is again pandemic period. So there also almost 1,40,000 vehicles are sold out. So government is believe that this plug-in type is a green vehicle. So for that, they are setting it to register at least 5 lakh vehicles per annum for each state. So for that, they are giving several attractive schemes. For example, you want to purchase, they will give incentives. Suppose you are availing loan, then it is interest free. Then if you are paying a cash, you will get a cash back. So likewise, they are putting several attractive schemes to promote this e-vehicle. But in the reality situation, this is the e-vehicle charging from the charging station, but the electricity is produced from the diesel generator. Even though it is a e-vehicle, but still it is indirectly polluting the environment. So then how we can make a perfect e-vehicle? Green vehicle. So for that we have to consider the energy source. So these are all the non-renewable energy source. So our energy demand almost 20 terawatt per annum at the moment. So if we make use of these natural resources, these will be going to exhaust soon. So alternatively, we have to use this renewable energy source. So the wind energy have the capability of fulfill the current energy demand, but however, it is seasonal as well as regional. So it's like you won't get the wind throughout the year, so you are unable to produce electricity throughout the year. But alternatively, you consider the solar. Solar, India is a sunlight abundant country. So we have to consider this particular solar for making the perfect green vehicle. So this is the first option. So the second option, hydrogen. Hydrogen is alternative to fossil fuel. It has that high energy density of 140 megajoules per kilogram. It is a clean fuel, so it can easily produced from water. So it's like it is a hydrogen is a earth abundance, and while producing hydrogen, there is no hazardous substance produced from the water. Then you can easily store it in different format. Like you can store it as a gaseous format, liquid, or a solid state. So it can be used for long distance transportation. So these are all merit of the hydrogen. So you just look at this, the hydrogen having different color code based on the origin of the starting material and the method of production of hydrogen. So you just look at this, there is a three methods will be used to produce hydrogen: electrolysis and steam methane reforming, coal gasification. So in the coal gasification, we are using coal as a starting material. While producing the hydrogen, it emits the carbon dioxide into the environment. So that emitted carbon dioxide, as such, if you leave it, it is called black hydrogen or brown hydrogen. When we talk about the uh, hydrogen, the emitted carbon dioxide that can be captured and stored, then this kind of hydrogen production, it's called the blue hydrogen. So while you are using the natural gas as a starting material, so it will be subject to the steam methane reforming. It produces hydrogen as well as it releases the carbon dioxide to the environment. So this kind of hydrogen we call it as a gray hydrogen. So when we use electrolysis method, the electricity which we used for the splitting the water, that is generated from the nuclear energy, so that will create the nuclear waste while producing the electricity. So we call it as a pink hydrogen. So while using the renewable energy like solar or wind, if we are using means, then that electricity, if you use for the water electrolysis process, so it is called green hydrogen. Okay, so these are the color codes for the hydrogen. So you just now you look at this. This is the fuel cell vehicles. So it is fuel cell train running in Germany. Fuel cell truck. This is Toyota America running in Japan. So this is zero emission bus running in United States of America. So this is Hyundai truck. So these are all e vehicles only, but they will use starting material as a hydrogen for producing the electricity. So I will just explain how this fuel cell vehicle is works. So this is the cross-sectional image of this particular vehicle. So it contains one battery, one hydrogen storage tank, then fuel cell stack, boost converter, power control unit, and there is a membrane that will allow only oxygen from the atmosphere. So once you ignite the vehicle, what happen? This hydrogen from the hydrogen storage tank, it reaches the fuel cell stack. Oxygen from the environment that will reach the other side. While combining hydrogen and oxygen, it will produce water as well as electricity. So here the byproduct will be the water. So it will be discharged as this one. So when we talk about the mileage, if you fill the 1 kg of hydrogen, you can drive up to 100 km. So you just look at this, the comparison between the Toyota America and Honda Clarity. So both will be FCV. So this FCV have that mileage almost 100 km per kilogram. So this is that fuel cell unit. So it contains one anode and one cathode. So when we open the start the engine, so the hydrogen is reaches that the electrode surface, and the proton is converted into hydrogen is converted into proton, and it releases the electron. That electron will be collected as electricity. Then this proton it absorbs the oxygen, and it released as the water as a byproduct. For your better understanding, I will show you a small video. Then you will come to know that how this fuel cell vehicle works. Is the videos visible? Sir, is the video?
Yes, sir. It's visible, sir.
Okay.
வேணாம்ப்பா வேணாம் வச்சுக்கோ உனக்கு ஏதாவது தேவைப்படும்
Sir,
Yes, ma'am.
sir, you have muted your mic. Please unmute it, sir.
What is that, ma'am?
Your video volume we couldn't hear, sir.
There is no volume, madam.
Okay, sir. Okay. Thank you.
So if we have hydrogen, we can run a 100% perfect green vehicle for the mobility purpose. Okay, so this is the advantage of this fuel cell vehicle. But when we're talking about the advantage, suppose if we compare with this plug-in type E vehicle, what happen? You want to charge one time, you have to wait 2 to 3 hours for complete charge for driving 400 kilometer. But here, 3 to 5 minutes, you can fill the 5 kg of hydrogen. You can drive up to 500 kilometer. So that is the another merit of this. So whenever talk about the advantage or merit of the system, we have to see that the limitations or drawbacks. So you just look at this: the hydrogen is highly flammable. There is a one time the Toyota Mirai car get accident, so the hydrogen storage tank got exploded, so it immediately catches fire. There is another incident in Norway. Due to the improper handling and the storage of the hydrogen storage tank filling station got exploded. Then
Excuse
later,
me, sir.
yes,
Excuse me, sir. Sorry to interrupt. It requires high pressure requirements, no, sir. So, as storing of hydrogen and safety related issues, how we could handle also, could
yeah,
you?
that's why I am going to explain.
Okay, sir. Okay, sir.
Okay.
Sorry.
So later, all the vehicles companies they have done R&D. Then because it is a high pressure only, so we want to store it. So you need a excellent storage tank. So that will be developed with that layer by layer structure. So especially they have high density plastic, one layer inner layer. Then after that, carbon fiber composite, so that will prevent catching the fire. Then glass fiber composite, that is one more layer. Then polymer foam. Then finally the fire resistant composite material at the top to protect this one. So for the mechanical pressure, for mechanical strength, they use the polymer foam and this kind of different layer by layer structure to avoid the explosion as well as the catching fire. They use the flame resistant composite material. So finally they have end up with this one. Then later they have done crash test. So this time the car got physical damages only. This hydrogen storage tank doesn't get exploded. Okay, so you may ask, sir, if any technology that will be introduced in abroad, it will take at least 10 to 15 years to reach in India. So when we will have this kind of technology. So for that, our CSIR Secre, we have developed the this zero emission bus with the our materials available within India. Then we have developed this technology and transferred to the Sentinel Labs. Then later, this technology is extended to Tata Motors. So Tata Motors, they have offered 20 buses to the IOCL employees. So especially you just look at this. This is in the year 2019. They have dedicated of some 5 buses to that Indian Oil Corporation Limited employees. So here it is written that hydrogen fuel cell bus. That means you may have that any kind of hydrogen, you can operate this bus. But when we talk about this, this bus is 2023. They have offered to this employee. So it's like here itself it is written India's first green hydrogen fuel cell bus. It seems here what are the hydrogen you are using? That is only green hydrogen, not blue hydrogen, gray hydrogen, or pink hydrogen, whatever it may be. But the previous case, you can use any kind of hydrogen. So that is what the difference between these two. So the primary idea, so actually they have 1,200 employees. So they, if we want to come all the people through office, then you need a parking, need a big parking space. So for that, rather than going for this, so you can accommodate at least 50 to 60 people here. So this is for representation purpose. I just to put this picture here. It is not real one. So it's like so you can reduce that pollution. Okay, reduce the pollution. Also, you no need such a big parking space and other things. So that is the idea. Then we have extended our stories to Cochin. So it is a marine metro. So the Asia's first marine metro is located in Cochin only. So previously, this marine metro is powered by battery. So that is plug-in type marine metro. So now, last year, our Prime Minister flagged off this hydrogen fuel cell powered passengers catamaran for a public utility. So if you visit Cochin, you may see this the hydrogen powered this one. The technology is developed by CSIR-Central Karaikudi in collaboration with the NCL, our sister concern lab, CSIR NCL Pune. Then we just working on this fuel cell vehicle next to for the track. So it is expected 2027. You may see that the fuel cell powered trains that will be available in India on the track. So that is. So now you may ask, sir, you are switching all the road transport and water-based transport and track-based transport to fuel cell vehicle. So if you switching all these things to fuel cell vehicle, then what is the fate of existing diesel and petrol-based vehicles? Uh, you may ask. So for that, recently, Ashok Leyland company, they have modified the engine, diesel engine, by using some other techniques. Then they have started using hydrogen powered truck. This is not a e-vehicle; it is a normal vehicle. But here you can, this is hydrogen based IC engine. Okay, so it's like a this IC engine based system. You can modify the existing diesel or petrol based vehicle to modify to this kind of operation. Then you can make use of this hydrogen for you can use for the transportation purpose. I just saw a short video how this modified trucks that will works. Madam, tell me if you are not able to hear the
Sure, sir.
volume.
Okay, sir. Okay.
On the road that leads
Ma'am.
Kekku, sir.
to the dream of greener mobility, the world now gets a new set of wheels to steer that journey towards reality. Presenting Ashok Leyland's pioneering technology, the hydrogen internal combustion engine vehicle that's built on the Avatar modular platform. The fuel delivery system on this vehicle is modified to use green hydrogen instead of diesel. A strong carbon fiber composite cylinder ensures safe storage and high pressure endurance of up to 350 bar. That's extremely easy to install, lightweight, and maintenance free. With minor changes to our H series 6-cylinder internal combustion engine, we are able to deliver power and torque equivalent to a conventional engine. With a lean combustion strategy, it ensures minimal emissions and less noise, resulting in an efficient, cleaner, and a quiet drive. The hydrogen internal combustion engine vehicle delivers the highest payload and long range. Its aggregates are similar to a diesel vehicle, aiding easier maintenance, all while complementing the hydrogen mission that supports the Atmanirbhar Bharat initiative. These benefits make hydrogen internal combustion engine vehicles a perfect vehicle to drive us towards the future. अशोक लेलैंड कोई मंजिल दूर नहीं.
So now you have an option for either EV based fuel cell vehicle or hydrogen powered trucks. So you have EV or non-EV based mobilities available in India. Okay. So, but if we are shifting our all the transportation to this hydrogen powered system, then what is that original hydrogen demand? How much the hydrogen is required? So that we will see. So now we are in the middle of 2020 to 2030. So at the moment, approximately 100 million metric ton of hydrogen is required. Suppose, as already pointed out, in the year 2050, where we are going to achieve that net zero carbon emission as per the Paris Agreement. So here you need a 539 million metric ton of hydrogen. Especially in the transportation sector itself, you need a 150 million metric ton of hydrogen. That is almost twofold higher what we are already consuming. So that much demand. So here you may see this now the hydrogen having opened the application in one sector, that is in the industrial sector itself. But in the year, if you move to 2040 or 2050, you may see this different colors. So it means the hydrogen not only in the transportation sector, it will be in a different sector for producing the electricity. So that's why the this much hydrogen energy demand uh, happen. So now let me see. So this much hydrogen demand. So how we are going to meet this much hydrogen demand? So that let we have to see. So what is the technologies available for meeting hydrogen energy demand? So it seems so we always evaluate the technology maturity through the TRL scale. So TRL scale is nothing but technical readiness level. So if we say that the TRL level number, then we will assume that his research areas this much. For example, TRL 1, 2, 3. So it is a basic research at lab scale. For example, if you have student doing some project and submitting thesis, so that is TRL 1. So the same thing, if you quantified and try to communicate to journal and publish in this one, then TRL 2. Then if you are going with the pattern or something, that is TRL 3. So this 1 to 3, it's all in basic level, that is academic level, just knowledge development. But when we talk about TRL 4 to 6, so here you have to scaling up that process, and you have to develop the technology. So that is TRL 5. So the same technology is demonstrated in collaboration with the industry. So that is TRL 6. So if you go to that the TRL 7, TRL 8, TRL 9, so these are all technologies highly matured one. That means you want to commercialize some product or something, and you want to send it to market. So you will evaluate how much profit we have to make it, and it's like if you are getting bank loan, how much principal, how much interest, then building cost, building rent, machinery cost, then human salary, marketing, then income tax, all will include. Finally you are fixing the price. 1 kg of hydrogen is 250 rupees. In a finite value, if you are fixing and send it for market, that is the high TRL level. So these kind of high TRL levels, it's only available for steam methane reforming with the carbon capture. That is the blue hydrogen. So autothermal reforming, gray hydrogen. Coal gasification with the carbon capture and storage, that is also blue hydrogen. So these are all blue or gray or these things. But we need a green hydrogen. Why? Because as per the Paris Agreement, you should not release any carbon footprint in the year 2050. If you go with that, the maturity technology such as steam methane reforming, coal gasification, we cannot fulfill the net zero goal. So for that, we just look at this now. The PEM based electrolyzers So this kind of electrolysis process just reached that the matured state, like it's in the transition of technology demonstration with the industries. But when we talk about the solar to fuel, that is solar to hydrogen production, that is in TRL level 1 to 3, that is still in infant stage. That means it is in the lab scale level itself. So that means we have to give more intention to bring out this TRL level above 3. So we are working on that. Okay, so these are the technology available. So for that, our honorable Prime Minister, he announced National Green Hydrogen Mission. So the objective of this mission, India to become a global hub for green hydrogen production and the export. Okay, so for that, initially they have announced the 800 crore budget. Then our Union Cabinet in the year 2023 approved the budget of 20,000 crores for this green hydrogen production related activity. So the expected deliverables by 2030 is nothing but we will increase that green hydrogen production capacity 5 million metric ton per annum, because we are using electrolysis method. So accordingly we can increase the electrolyzer capacity up to 100 gigawatt. Then we are using the renewable energy for electrolysis purpose, so it requires less amount of electricity. The excess electricity that will be connected through the grid, so this grid that will be increased to 125 gigawatt of energy. So these are all direct deliverables. So the indirect deliverable, if we are moving to fuel cell based vehicle, we will not go into use diesel or petrol. So in that way, we can stop the import of crude oil worth of 1 lakh crores. Then, as per the Paris Agreement, every year 50 million metric ton of CO2 emission that will be stopped. Then it will create a 6 lakhs job opportunity and 8 lakhs crores investment, corporate investment towards green hydrogen related activity. I will give one typical example for the last two cases. So last year, our chief minister visited to United States of America. So there he signed the agreement with that company name is called Omium. So the Omium is the green hydrogen production company. So they are having two plants in India, one in Bangalore, another one in Chengalpattu. So they have signed the agreement. They are ready to set up another plant at Chengalpattu with the worth of 400 crores. That will create 500 job opportunities for the individuals. So this is what this green hydrogen related activity will help to make it. So it's like this is the MOU signing ceremony. So this is the guy Chokalingam. He is a chief technical officer from this Omium company. So he is the alumni of our CSIR Karaikudi. So he completed BTech with our institute. Then he moved to USA. So now let me come to that original story, how we can use the sunlight for producing the hydrogen. You just look at this, this is the simple chemical equation. So that means you just take a water, you add a semiconductor exposed to the sunlight, it will produce hydrogen and oxygen. So here you just look at this simple equation involves two reaction. One is hydrogen evolution reaction that involves 2 proton, 2 electron. Another one is oxygen evolution reaction. It involves 4 proton and 4 electron. So involvement of this 4 proton, 4 electron, we call it as a rate determining step. Overall, you want to split the water, you need 1.23 volt theoretically. So how this semiconductor can produce hydrogen? You just look at this. This semiconductor have valence band and conduction band here. So once we apply that incident photon over here, the energy is higher than the band gap. It will create a holes here, and the electron is moving here. Then this holes oxidize the water and produce oxygen. Then proton. This proton is moving here, and it accepts the electron. Finally, it produces hydrogen. Okay, so in this case, this simultaneously it will produce hydrogen and oxygen. So we call it as a bifunctional catalyst. Suppose you may ask, sir, what happened? The valence conduction band is below to this hydrogen evolution potential, or the valence band is above to the hydrogen evolution potential. So in this case, you just look at this. This is the two case. So here it will act as the oxygen evolution catalyst. Here it will act as a hydrogen evolution catalyst. So this is what if the band position is not matched properly, then it happen like this. But the problem when we use this photocatalytic method, so here you will get a mixture of gases, hydrogen and oxygen. Then you need a further separation, gas separation, it's required. Okay, so in this case you just you have to think the same working principle in different way. So for that, this Honda and Fujishima together, they have designed this cell. It is a photoelectrochemical cell which consists of one anode and cathode. The anode is made up of semiconductor, so both will be connected through the circuit. Once you expose to the light, what happens? The semiconductor oxidize the water and it produces oxygen. So that oxygen collected separately and it will produce proton. That proton passes through the proton exchange membrane and it accepts the electron here, and it reduces it to form a hydrogen. So the hydrogen you can collect it separately. So this is what the same photo induced process that specially designed this cell that will facilitate that the gas separation. So that is the merit of this photoelectrochemical method. So usually the semiconductors are two types. So one is N type and another one is P type. If you have a N type N type semiconductor, you can use it as a photo anode. Suppose if you have a P-type semiconductor, you can use it as a photocathode. So here it will be used for water oxidation. Here it will be used for water reduction. So suppose you are having the tandem cell, you can simultaneously produce hydrogen and oxygen by using the photoanode cathode. Suppose a person want to start the person want to start and work on this photoelectrocatalytic water splitting, he or she must be consider these four criteria. The first criteria, suitable optical properties. So the suitable optical properties is nothing but the solar spectrum having three different type of rays. One is UV ray, visible light, and IR radiation. If you use UV light, it is only 6% in the spectrum, then it is inefficient method. If you use IR radiation, that will produce heat energy, so that won't be apt for this particular application. So you have to choose the material which can absorb in the visible light. So accordingly you have to choose the material. Then the second criteria for screening the material, suitable bandage alignment. As already pointed out, this conduction, this valence band and the conduction band, that should be apt position. Otherwise it will act as a only HER catalyst or OER catalyst. So you have to find the band position before choosing for this purpose. Again, charge separation and transport. The charge separation transport means once it is exposed to the light, what happen immediately, it will undergo charge separation and the electron have migrated to current collector. So this is what you have to see the charge transfer kinetics. Then the stability, because you want to make a commercialization, it should have that highly stable one so that you can do commercialization. So you have to consider all the four criteria. Okay. So our interest, we are using different type of materials. So our interest, business based material. So the business material that will be categorized into four types. One is single component, binary component, ternary component, and other compound. So in this way, you just look at this. So our interest is this kind of ternary compound. So why? Because the bismuth-based material, which has that more positive than the oxygen evolution potential, so that it is more beneficial for water oxidation process. So this water oxidation kinetics is a rate determining step. If we are easily oxidize the water, you can enhance the hydrogen production rate. So that is the one. So that's why our interest. But when we use that this pristine semiconductor, what happened? This performance is get quenched because of the charge recombination process. To overcome this limitation, you can do component adjustment, or you can do surface modification with the conducting material, or you can tune the morphology, or you can form a heterojunction. So this our interest is a heterogeneation strategy. So you just look at this. We are doing the heterogeneation. Why? Because you just look at this. A person is jumping from the ground, and due to the gravity, he is fall on the ground. Okay. So likewise, if you take a single semiconductor, upon irradiation, it will undergo charge separation. Due to the Coulombic force, this electron and holes will be recombined, and net result will be zero. But at the same time, you just look at this other picture. You can add one table or chair, then you can jump and stand on this one. You are spatially separated from the gravity. So likewise, you can add another semiconductor. So here, what will happen? The electron will be stepping out, stepping down, and the holes will be stepping up. So the electron and the holes will be spatially separated here. So the process is very efficient. So the heterojunction that can be classified into three types. So the one is a straddling gap semiconductor type, another is staggered gap, another one is a broken one. So type 1, type 2, type 3, all will be based on the band position of the neighbor semiconductor. You just look at this. So here the electron and holes will be move in the same direction. Here the electron and holes will be move in the opposite direction. So this is the broken type. So it is very difficult to transfer the electron. So it is predicted one, but by practically it will not be in use. Other than that, you already know that the semiconductors are two type. One is P type and N type. So both, if you combine P type and N type semiconductor, you can form a PN heterojunction. So once it is comes to the contact between these two, it will create an internal electric field at the space charge region. As a result, the holes will be stepping up and the electrons will be stepped down. So the oxidation takes place at P type, and the reduction will be takes place at the N-type semiconductor. So other than that, sometimes if some reactions are thermodynamically is not favor, then we can go with the eject scheme mechanism. You can add one mediator, then you can stepping up the electrons and stepping down the holes. So this is the best way for perform this one. So it is a mediator based eject scheme mechanism. This is a mediator free eject scheme mechanism. So you may see this, there is a plenty of materials reported for the photoelectrocatalytic water splitting for green hydrogen production. So you just look at this, the band positions are suitable. So likewise, there is a metal oxides, metal nitrides, metal chalcogenates, everything that contains the metal, all the catalyst. But there is one catalyst which is called GC3 and 4. It doesn't have any metal, so it is a metal free semiconductor. So this is the G3 and 4 structure. Actually, it is a two type. One is a heptacene based, another one is a triacene based graphite carbon nitride. So it is visible light absorbing capability, and also it is a metal free, non toxic, low cost, and you can easily tune the structure. So these two structure is predicted by Berzelius and Leiby. Okay, so you just look at this. This is the triacene based one. This is the heptacene based one. So here, this is highly stable due to the extended double bond, more number of double bond here. It is less stable, and it is this is preferred to form at all the time during the synthesis. So this can be synthesized via two methods. One is a top-down approach, another one is bottom-up approach. Okay, so this top-down approach, you just take a bulk material, then you can do exfoliation. Finally, you'll get a nanosheets. Then bottom-up approach, you can take molecular precursor like a melamine, cyanamide, dicyanamide, urea, thiourea. Then accordingly, you can heat it up to 500 to 550 degrees Celsius. Then finally, you will get a heptacene-based graphite carbonate. You can see this yellowish color. It has that tendency for absorbing the visible light region. So this is the formation pathway for this graphite carbon nitride through different methods. So it's like a you can go with this. So you can if you take a cyanamide, then it will form a dicyanamide. Then dicyanamide become melamine, melamine become melium. Then finally polymeric form. It is. So you can easily tune the structure by adopting different methods and you choosing the precursor and the templates. Accordingly, you can tune that the structure as well as the surface area. So both will be this one. So I will just show one example for this graphite carbonated bismuth heterojunction for photoelectrolytic water splitting. So for that we have taken melamine and mixed with ammonium sulfate and mixed for some time. Then it will subject to the calcination at 520 degrees Celsius for 2 hours. Finally, we got the nanostructure. Then we have taken the molybdenum and bismuth precursor in ethylene glycol. Then we have added different weight percentage of graphite carbonate subject to the solvothermal treatment. Finally, we end up with the heterojunction material. So this is the epichem image of pristine bismuth molybdate. This is after the incorporation of graphite carbonate over the surface. So you may see this hierarchical structure got disturbed due to the addition of this graphite carbonate. So we have done elemental mapping to confirm that the existence of different elements like bismuth, molybdate, oxygen, nitrogen, and carbon that we have confirmed with the elemental mapping analysis. Then the XPS analysis, which support for that the shifting in the binding energy for the this composite material, which clearly reveals that the formation of heterojunction between the two interface. So that clearly evidenced from the XPS analysis. Then for the crystal studies, we have done XRD pattern. So you just look at this. So this is the graphite carbonate. This is bismuth molybdate. So after the addition of this graphite carbonate, this orthorhombic structure of bismuth molybdate doesn't get disturbed. So this is the XRD pattern obtained for the different weight percentage of graphite carbonate. Then the carbon nitrogen functionalities present in the prepared materials that will be characterized by using the FTIR analysis. Then we have tested the surface area analysis. So you just look at this. When we use the pristine material, it shows that the least surface area. When after making the composite, it shows that the high amount of this one the surface area got increased. Excuse me, there is one urgent call. Hello.
Yes. Okay, sir. Okay, sir.
Hello. Ama. 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 சரிங்க. ஓகே. So then we have done the contact angle measurement to check the suitability of this material which interact with the water. So if you use this graphite carbonate, it shows least contact angle. If you go with that bismuth molybdate, it shows that high contact angle. When we make that this graphite carbonate bismuth vanadate heterojunction, the contact angle lies between Gc3n4 and bismuth molybdate. Why? Because this bismuth molybdate hydrophobic in nature. So if it is a hydrophobic, means it will not interact much with the water. Then while we are doing the water splitting, it won't give a better result. So for that we made this composite. Then we got the moderate this one. This is a hydrophilic nature. Why? Because it has that the hydrogen. So that will make the hydrogen bonding between this graphite carbonate with water. So accordingly, it shows that the better activity. So then we have tested the optical property and measured the band gap for this. It found that when we are changing this graphite carbonate weight percentage, the band gap also slowly alter. Then we have tested the performance in the dark condition for the prepared materials. So it shows that the least response in the dark condition. So upon we are switching the we are exposing to the sunlight, what happened? The photocurrent density got increased. So the pristine material shows that poor response, but when we talk about hybrid material, it shows almost 25 microampere current. So we have optimized this one. So we varied this one. So we found that while changing this graphite carbonate, that will alter the graphite carbonate that will alter the performance. So then we have choped the illumination for to check the stability. So it seems that the rise and fall in the photocurrent for several cycles, it is highly stable and reproducible. So it fulfills the stability criteria. Then the efficiency also we have calculated the 10% efficiency, 10% graphite carbonated, which shows that high performance as compared with the pristine one, that is 7-fold and 20-fold higher than the pristine material. Then we have collected the band positions value from the literature. Accordingly, we have derived the band position. Then finally, we proposed the type 2 heterostructure for water splitting application. Then there is another system. The previous case, we have prepared the material as a powder form and fabricated electrode. So there is another case, we have fabricated the electrode through the thin film deposition method. So for that, we have done the electrode deposition of bismuth vanadate over the electrode surface first. Then later, we have deposited copper oxide over the surface. Then finally, we got copper oxide PN heterojunction structure. So this XRD pattern clearly reveals that the presence of the peaks due to that copper oxide and bismuth vanadate on the FTO plate surface. Then also we have done that the morphological studies by using the FECM analysis. So this is the pristine bismuth vanadate. This is after deposition of copper oxide. So the elemental mapping, it's clearly confirmed that the existence of bismuth, vanadium, oxygen, and copper in the heterojunction electrode. Then the XPS analysis, as usual, we have recorded, and it clearly shows that the shift in the binding energy after deposition of copper oxide, that clearly reveals that the formation of heterojunction between the two semiconductor interface. As well as we just to look at this is absorption spectra, which shows that visible light absorption for bismuth vanadate got increased after deposition of this copper oxide over the surface. Then we have calculated the band gap for bismuth vanadate and copper oxide through Tox plot method, and the values 2.53 and 1.47 electron volt. Then we have performed the photoelectrochemical water splitting performance in the dark condition. It shows that there is no current response. So once we expose to the sunlight, it suddenly the current is increased for the pristine material. Then after forming the heterojunction, it shows that further enhancement in the photocurrent. It is almost twofold higher than the pristine one. Then we have want to study the starch transfer mechanism. We have done UPS analysis for both valence band UPS analysis for both bismuth vanadate and copper oxide, and Fermi levels also we have evaluated through the Markov analysis. Finally, we have substituted all the values in this formula. Then we have arrived this band position for the both semiconductor. This is before contact. Once it is comes to the contact, produce internal electric field at the interface of this PN junction. Then finally it oxidizes the water and it produces hydrogen. So the stability and efficiency also we have calculated. It shows good stability and it shows 0.3 percentage efficiency for the best performing material. So we have done some of the work in our lab on this photoelectrocatalytic water splitting through the powder processed method. So for example, some hydrothermal method, we will prepare this kind of catalyst, then coated over the electrode, then we study the performance. The second some case, we have prepared this material as a thin film through the electrode deposition method. So you just look at this here, or the values and response, the all in microampere scale. It is in the milliampere scale. So it seems like a 1,000-fold enhancement in this photocurrent density, as well as the efficiency. Also, we reached the benchmark efficiency closer to the benchmark efficiency, and we achieved high catechism production rate. Then what are the results you have seen until now, and in the you are seeing in the lab this tabular column? It's all TRL3 at lab scale investigation. So now I want to go one step further. So now you may recall. So what are the results you have seen in these previous slides? That will be TRL 1, 2, 3. So now we want to go for TRL 4. So that I will explain how we are going to achieve. So we have concluded that the best method for fabricating electrode is the electrode deposition method that will give good performance. Then we adopted the same method. We are start from 1 centimeter square to 25 centimeter square. So what are the results you have seen in the previous slides? That will be done with this 1 centimeter square. So now we are scaling up this electrode from 1 centimeter square to 25 centimeter square. So this is the bismuth vanadate. So it is a plain electrode type. So this is the prototype device we have developed with this. With this. So you may see this. It's like we are using the quartz window as well as the Nafion membrane for the fabrication of this prototype photoelectrochemical cell. Then we have tested the performance, everything. So now I will show the value. When increasing the area of the electrode, the current response is keep on increase. So I just want to look whether this 25 centimeter square electrode, it's behave like a 1 centimeter square electrode. Actually, by visually, if you are looking, means it shows increasing the current. So that means, for example, 1 centimeter square can capable to produce 100 hydrogen. Then 25 centimeter square should be produce 2500 hydrogen. Okay, but it seems this won't be produce 2500 hydrogen. It will produce only 1000 hydrogen. Okay, but when we talk about the increment, it's look like a increased, but it's not actual increment. So that means you are having the losses somewhere. So that to prove that one, I have convert this this current into current density. That means now I am converting this 25 centimeter square electrode performance like a 25 into 1 centimeter square electrode. Like that I have assumed and calculated. Now if you look at this, the trend will be reverse. So previously it's top to bottom, now top to down. So this is what it's like the increment happen. So I just want to see. So I don't know why it's happened. Then one day I was scrolling in the Facebook. Then I have seen this kind of cartoon. Then I asked my student to fabricate the electrode, these kind of things. So for that we have done the silver paint coating for conducting lines, for making the grid lines, everything. Then you just look at this. This is the performance photoelectrochemical parameters for the different dimension of electrode. So if we start 4 centimeter square, it have the 20% loss. If you go with 934, then 16 means 60 means 41% loss and the efficiency. Then if you go with 25 centimeter square, almost 50% loss in the photocurrent. So we have modified the electrode. So if we use plain electrode with the different dimension, so we are having the issues. Then we have modified the electrode like a line pattern and grid pattern. So now we just analyzed the performance. So you just look at this pristine plain electrode, it shows 51. When we use the line pattern, it shows the 41%. Then when we go with the grid pattern, it is 27%. Almost we have reduced half of the loss of this photocurrent density percentage. Further, we have added sacrificial agent into this. Then we have enhanced the we suppress the loss to less than 20%. When we go with the prototype device, if you are having the loss in less than 25%, that is the affordable one. So we have filed the patent on this. So we have checked the hydrogen production rate with the different applied potential, and also we observed this increase in the performance. So also we checked the durability. So it shows that the high durable. So this is the summary of presentation. So initially I have discussed the hydrogen, the importance of hydrogen, and how the hydrogen can be classified into different color code. Then the method for producing the green hydrogen by using the photoelectrochemical methods, and the materials which we developed in our lab related to the heterojunction, and the materials performance in the photoelectrochemical water splitting at the lab scale. At the end, I have discussed the prototype development and its performance for the green hydrogen production through this photoelectrochemical method. So this is the overall summary of my presentation. So one of my students received best thesis award for the pioneer work in this photoelectrochemical water splitting, what I have discussed in the lab scale level. So this is the journey from lab scale to prototype. The publication, these are the publication we have done on the lab scale level and published in papers. So you want to know more about this heterojunction material, you can send a request. I can share this book with you. Then this is another recognition. We have participated in the conference organized by Office of the Principal Scientific Advisor to the Government of India. So there we bagged the third prize for the green hydrogen production, and one more recognition is received by my student for her contribution in the green hydrogen production. She got selected and nominated by the DST New Delhi to participate Linda Noblat meeting, which was held in the Germany last June and July. She is one among 29 Indian young scientists, especially she is one among the 3 in the chemical domain, chemistry. So finally, this is the acknowledgement. Without funding support, can't do any cutting edge research. And finally, I thank all the team members. Thank you for this is the take home message for today's talk.
Sir,
Yes,
thank
madam.
you. Thank you so much, sir. Awesome, and hats off to your work, sir. Really, really very challenging and imposing work, sir. Thank you for sharing your experience with us, sir.
Thank you, ma'am.
Sir, I have a doubt.
Yes, ma'am.
While going in for hydrogen storage, you said you have to have 6 layers.
Yes, ma'am. Yes, ma'am.
6 layers of for protection and for safety reasons. You said you have to make them in 6 layers. Then how about the cost, sir? Actually, already the fuel cost is like it is rising like some. Then how about hydrogen cost? Could it be affordable for common people?
Yes,
Or
ma'am. Actually, we are planning to bring the cost to 1 kg of hydrogen for 250 rupees.
1
Now
kg of
it is
hydrogen.
$4, madam. $4 per kg hydrogen. So
Yes,
in
sir.
India, we are planning to give 250 per kg. So 250 per kg means per kg you can drive 100 kilometers.
Actually, we too in our college we try to generate a triple energy storage system, wherein we tried with the fuel cell, hydrogen energy fuel cell we tried, sir. But due to the compatibility and the we cannot store or we cannot use hydrogen in practical application. We are due to cost and other factors.
Actually, this hydrogen storage tank is available in ready-made. Even you can buy as per your requirement. So it is available in the market. So
Okay, sir.
You can find the right vendor to you can get it and use for your applications.
Okay. If any queries or doubts, I'll surely contact you for.
Okay, sure, ma'am, sure. Always welcome, ma'am.
Thank you for sharing your eminent knowledge in this area, sir. And truly an insightful presentation. Thank you. Thank you so much, sir.
Thank you, ma'am.
Participants, you have any queries? Kindly post it in the chat box.
Yes, if you have queries, please post it in the chat box.
Dear participants, you have any queries? Kindly post it in the chat box. Dear professors, you have any queries? Kindly post it in the chat box.
Thank you so much. Now I invite Dr. D. Periyalaga sir to propose the vote of thanks for today's session.
Thank you, ma'am. On behalf of organizing committee, I express our sincerest gratitude to Engineer Pandikumar, CSIR CECRI for delivering an informative and impactful session. His in-depth technical insight, practical explanation, and real-world perspective significantly enhance the learning experience for all participants. The clarity with which he presented the concept and addressed participants' queries made the session highly engaging and valuable. We are truly thanks to Engineer Pandikumar sir for sparing his valuable time, sharing his expertise with us. We also extend our sincere appreciation to all participants for their enthusiastic participation, which contribute greatly to the success of this session. Once again, we thanks to Engineer Pandikumar Sir, CSIR, CECRI. Thank you for making enriching session today. Thank you, sir. Once again, thank you so much, sir, for your valuable session.
Thank you, sir. Thank you. Thank you all.
Yes, sir. One more information for the participants. We can enhance our knowledge with Dr. Pandikumar sir because he'll be presenting one more session that is scheduled on 19th. So we don't need to worry. We can enhance our session in the 19th. Thank you so much, sir.
Okay. Ma'am, I am leaving now.
Sir, once again, sir,
Sir,
we need a group photo.
Could you turn on your video, sir? So
Yes,
could
sure,
we take a screenshot, sir?
Sure, ma'am.
Dear participants, kindly unmute your videos. We had a photo session. Dear participants, kindly unmute your videos. Please, professors, kindly unmute your videos. We had a photo session.
Ama அது எந்த மூவில பிரதர்?
Thank you, dear participants. Please fill the feedback form posted in the chat box. Then you have to leave the meeting.
Thank you, sir. Thank you all. Thank you all for your
Thank you all.
patience.
நீ தான்
நீங்க கொஞ்சம் கூட